Okay, so is my screen visible?
Yes, sir.
Okay. So in ensemble methods, we will be covering bagging and boosting. Okay. So what happens in bagging? Uh, Actually, in any ensemble methods, we train some m numbers of estimators and we try to combine their outputs. That's why the words ensemble comes. So here we will be having two algorithms. One is bagging, second is called boosting. So in bagging, we train those estimators independently, and on a given on the data set. From the data set, we try to come up with some m different training data set using some methods and using some sampling method called bootstrap sampling. And over those m different training samples, we train some m different estimators and then combine those results, right? That we have seen in the theory part, right? Bagging. And in boosting, what we do, we start with a weak learner and then we boost its performance based on the what error it makes or what error the last estimator makes on the training data set. Based on that error, we try to boost its performance, and that algorithm is called boosting. So in bagging, we will be covering random forest, and in the boosting, we will be covering ADA boost. Okay. So along with the course, we'll briefly summarize everything there, and then we'll do the coding from using NumPy library. Okay, so let's start with bagging. So in bagging, we'll be doing a random forest. So actually, bagging stands for bootstrap aggregation, where for training m different samples, we need n training data set, right? So we have given a training data set to create m different training data set. What we do, we sample from the given training data set. The same number of samples we collect from that training data set, but with replacement. So it makes sure that our training data set are different, right? Those m training data sets are different in a particular bag. That training data set we call as a bag. So in a particular bag, there are chances that 33% of actual data set doesn't end up selected in this bag. So on an average, 60% of the training data set comes into a bag, right? So in that manner, in that doing bootstrap sampling, we create m different training data set, and over those m training data set, we train our estimators. That estimators should tend to overfit. That is the first part of bagging. If they are not tending to overfit, or say they are not having high variance, then bagging won't be that efficient. Okay, so bagging actually reduce your variance of the estimators. So that is why decision trees with the full length are used in bagging. Remember, decision trees with the full length have high variance, right? Because each and every nodes try to split the data set, right? And it keep on splitting till it stops, right? Where we don't have any more splitting possible. So it keep on growing till end, and it may grow to the very large nodes, right? So a decision tree with the very maximum possible length is tends to overfit and hence very high variance. That is why generally decision trees are used in the bagging. You can use different estimators as well, but it doesn't make much sense to aggregate those results which are of same nature, or say which don't have high variance. So that is why decision trees are the preferred estimators for any ensemble methods. Okay, so it's not that you cannot use different estimators. You can use, but generally the estimators with the high variance are used in bagging. And in boosting, the estimators with the high bias, like decision stem, where they tend to underfit, right? So in that boosting, we use the weak learners, or call the weak learners are ones which have the high bias. Okay, so just focus on the bagging first, then we'll go to boosting. So in bagging, those m different estimators should have high variance. And other point is that those estimators should have different structure. I mean that though they should not output the same kind of outputs from for a given training data set. If they are doing they're predicting the same output, then doesn't make any sense to aggregate those results, right? Because ultimately you're not gaining any more information about the not gaining any further information about those outputs. So those structure of those estimators should be different. And remember, in the random forest, what we do, we grow the full size tree, right? But using some different samples of features. We don't make use of every features to split a node. We make use of some random sample of the feature to split a node. Just because we have, by doing so, we will have variety of trees, right? If we are training AM differently, those AM trees will have different structure because we are not making use of every features to split the nodes, right? And that is why, to make sure that those trees don't correlate to each other, we use the different samples of the features. Okay, so let's do that now. We will be doing random forest here. So in algorithm, if you have any doubts, you can ask. If not, we can move to the coding part. Okay, so first we are importing the libraries. NumPy library is mostly used here, and I've global variable I've set tree and tree list, because remember tree will be your one model, and in a random forest we will be creating such m trees, and we will take those in a list. We will store those trees in a list. So global variable I've set those. Now this is the dataset I've used for the training purpose. So the dataset has been used, is present in the SQL libraries. It's the cancer breast cancer dataset is available freely, or other site as well. You can get this dataset. So here X is your call is a the it's of shape N cross D. So if you check of shape of this, so this will be of across D. So there are 569 examples in the dataset, and 30 features are there. And or if you check the shape of by as well. So remember, 569 examples, so corresponding labels are 569. Right. So X is the data matrix, Y is the corresponding labels for that dataset. Okay. And if you check the dataset here, X dataset here, let's say some five values. So all are numeric values, right? So all the features are numerical feature. Nothing, no categorical features are used, are present in X. And similarly, if you check the values of Y takes only values 0 and 1. Okay, so it's a binary classification problem where all the features are not categorical. All the features are continuous features. Okay, so we will make use of this data set to train our random forest. Okay, so remember, in the random forest, first task is to we have to create different data sets, right? If we are training m different decision trees, then we have to create m different data sets. So for that, we will be using a function called bootstrap. Okay, so let me hide this one. Okay, so it will be called define bag. So in bag, remember we have the data set by and the corresponding labels, and every time we randomly select a we randomly pick the values from we randomly pick the data points from the X and replace it to select the next data points. And in such manner we pick n points, and we call that n points as a peg that will work as a training data set. So let's collect them, and we can make use of the libraries mp.random dot choice. So what it will do. So how till so I will collect first indices for that, and from using that indices I can take the data points, right? So these are my indices here. So indices will be starting from 0 to number of samples, right? Because from n samples you have to collect that. So let's call those as n samples. Number of samples as x dot shape. So n number of examples are there. So till that indices, I have to select some in this index, and how many such we want. How many such index we want? We want n, right? The same number of examples we want in every way. So this will be your n sample. And does the replacement is allowed here? The replacement is allowed in the bootstrap sampling, right? So these are the different index, and we are allowing the replacement as well. So what it should return, the bag should return your X data set, but now with this indices, right? And similarly, their corresponding labels. So if you call this function on our data set X and Y. So this is now your X and this is your Y. So it has collected some random data point from the original X and Y. Okay, so if you check the shape of this is again gonna be tuple. So let's call it 1 and 0 and 1. So now, so remember this again the same shape, right? Because in every week we have the same number of examples, but now we are allowing the replacement. So make sure that all training example doesn't come into the every week. Okay. So this is this is the code for creating your different training data set. So it should be not any doubt in this code. If not, we can move to the part. So this was easy. Okay. So now what we have to do, we have to train different decision trees over there, right? With the full length. So for this, splitting the decision tree, we need to split. We need a measure to split our data set, right? So we are using the function entropy here. So it's easy function here. Entropy takes the parameter p. P is the count of or say proportion of the data point which belongs to the label one, right? So if p is zero or p is one, that is that node is perfectly pure. It means that if p is zero, it means that there are only class zero examples, and if p is one, it means that there are only class one example. So that node will be pure, and in that case, entropy will be zero. Otherwise, if p is not zero and one, then in that case, the entropy will be minus p log p minus one minus p log p, right? Log one minus p. So this part is should not be a problem. So this entropy this measure we will be using for split our data point. Now next part is okay. So for to grow a decision tree, we for at a particular node we need to know which is the best point, which is the best feature, and which is the best point to split that node, right? And for that we will be using entropy or say information gain, the feature or the split point at which the information gain is the maximum. That feature or that split point we will be using for split our data point, split our node. Okay, so that function we have to write here. Okay, so let's call that function as best split. And we have already done this part in this one, week 7 as well. So that should not be a problem. If you have any more doubts, you can go to that session as well and see. So we denote a node by two things: one the data set and one the corresponding labels. So these two things will denote our node, the data set that is present in the node. Okay, now we have to come up with the best split feature and best split point for which the node can use to split the data set, right, into left and right nodes. Okay, so for that we will be using information gain. One more thing here I'm adding here is that we am you let me define it first. Next feature. Okay, so remember in the random forest, we don't make use of every features to split the nodes. We take some random samples of features, right? So I'm using that parameter. I'm giving that as a parameter how many features I want to split our nodes. Okay, so let's first call number of features. Total features in the dataset are x dot save one, right? These are the total number of features in our dataset. And how many the features that I want, I'm storing there here. So random features I want, right? So remember, features are denoted by its index: feature 0, feature 1 up to feature 30. If there are 30 features, so feature 0 to feature 39 will be our 30 features. Okay, so they are denoted by their indexes itself. Okay, so I'm just taking some random indexes to denote those features. So I can make use of that function again, random dot choice. Okay, so n features up to n features I have to take points, and the size of that will be it will be defined user defined parameter max features, right? this much features I want. And anything else, you have to make sure that they are not replacing, right? So replace I can set to the false. So this will give me the array of the features that I'm gonna use for splitting a node, splitting a node. Okay. Now, so what information I have to I have to find to split the node to check whether that is enough, that point can be split according to that feature and split point. What I have to measure? I need a measure, right? That measure that we are going to call information gain, right? So let's start with that. And so how to find that split point and how to find that split feature? We scan through every feature, and for every feature we scan through each and every possible values that that feature takes, right? And we check whether we check for what feature and what point the feature information gain is the maximum. We choose that point to that features to be the best feature, and that point to be the best feature to split our node. So what we will do here, we will go through every possible feature, we will go through every possible point, and we'll find that information gain value for every feature, and we'll store the we will pick the value for which the information gain is the maximum. So what we have to do, we have to scan for each and every possible value. So let's start for doing that. Let's start for let's call that feature. For feature in features, we'll go through every features, and for every feature we have to go for every possible values, right? So for well in let's call it it's every feature, so every point corresponding to that feature. Okay, so we have to find for information gain if we split that node according to that value and according to that feature. So let's store here those values here. Let me call dot ig west, and that best feature and the best value as initially I'm setting as 0. I can replace it with the best one, right? So these are my the best one initially. Next I will scan through every feature, and for every feature I will scan through every point. Now I have to find the okay, remember this is your parent node, and now you will split it. So for parent node entropy I can calculate here. So let's call that proportion p, the proportion of the data points which belongs to class 1 in the parent node. So that will be your by, where by equal to 1, right? So save how many examples, this will be the example which belongs to class 1, and the proportions will be by dot save, right? So this will give me the proportion of example which belongs to class 1 in the parent node. So entropy will be what, let's call it e. So it will be entropy. I can make use of the function entropy, this function entropy here with the parameter p, right? So this will be my entropy for the parent node. Parent node. Now we are splitting this node, and if we split according to feature this and this value, then I have to find the entropy, right, or information gain. What's happening? Okay, so let's call that entropy. Let's first we have to find what example belongs to left node and what example belongs to right child node, right? So let's call those as left. So in the left node, I will just collect those their corresponding labels, because those labels I am just worried about. So by will be in so for by where x according for that feature, if that value is less than or equal to that value, I will collect only those values, right? So this will be my left node, and in the right node, what will be there? I will collect only those labels for which the jth feature, I mean that feature value is greater than that value. Okay. Now this is my left node and this is my right node. If we split the point according to this feature and according to this value, right? Now I have to find the entropy for left node and entropy for the right node. So I have to make sure, let's call that proportions as q and r to be 0 and 0. So this is the proportions of the class 1 example in the left node, and this is the proportion of class 1 example in the right node. For finding entropy, I need those parameters, right? So if left dot shape 0 is strictly greater than 0, that is, there is some example belongs to left node and some example belongs to right node, though they are not the empty node, right? So if they are not empty node, I can replace q with q with the proportion of example which belongs to left node. So left node where the left is y, right, 1. So this is the examples in the left node which takes the class 1. So these are the examples which belongs to left node with class 1, and the proportions will be total examples in the left node. Similarly for R as well. So here it will be BST. Same thing. I'm taking the proportions of the examples which belong to right node with the class 1. Right. Now, what will be the entropy? The entropy for the left node will be, just call the function entropy, the parameter q, and uh, right will be same thing again, the parameter r, right? So this is the entropy of the left node, this is the entropy of the right node, and what we want to calculate the information gain. So let's call it Iz. It will be your entropy of the parent node E minus, I need gamma as well, right? Gamma will be the proportion which belongs to left node out of the total nodes, total example. So this will be the left dot shape. So these many example belongs to the left node, and the total example was, right, this will be my gamma. So gamma times left node minus 1 minus gamma times 1 minus gamma times right entropy. So this is the information gain. So if this information gain is the better one, I mean, if information gain is the higher than the previous information gain, then we will replace that Ig base with this Ig, right? So what I will do, if I will check whether this Ig is, if this Ig is greater than Ig base, I will just replace those values. I will replace Ig base with the current Ig and those split value and split value. So best feature will be what, your this feed, right, and the best value will be your this value, right? So what's happening here, we are scanning each and every features, we are scanning every possible values of for that feature. We are checking the IGs if we split the node according to that value. If that this information gain is better one, I mean that higher one with the previous one, then I will just replace it, because now I will be using that value or that feature to split our node. Okay. So thus I will keep doing scanning for every feature and every value, and the best one I will return, right? So what I will do, I will just return the best value. I will just return. So I will just return the best feature to split the node and the best value to split the node. So I've been given a node. Node is denoted by the data points, and it is returning the best feature and the best value. According to that node can be split. So this is the code for defining the best split of a node. So if you have any doubt in this code, you can ask. Otherwise, we can move to the next part. The same thing is done here. I've just shown the same thing. Okay, so if you don't have any doubts here, we can move to the next part. Okay, once we have the split, now we have to grow the full tree, right? Because we have only find a best split point and a best split feature for a particular node. Now we have to grow the full tree. So what we have to do, we have to recursively call this function till we got the pure nodes, right? And how we are going to store those nodes and store those information? We are going to store those information in the dictionary. And why we are storing? Remember, whenever a new data points come to make the predictions, we have to traverse that data point from the root node to the top bottom node to the leaves, right? From the root node to leaves. And that is how that is why we need entire information with us, how the each node is being splitted, and which are the leaf nodes, which are the internal nodes, and the internal nodes, what are the questions to split the node, right? So for we have to store those information somewhere here to make sure that for a unseen data point we can traverse our data point from the root node to the leaves. Okay, so that is why we need to store those information somewhere. So we will be storing those information in a leaf, sorry, in a dictionary. And actually the tree is a model, right? So we are actually training a model, we are growing a full model here. So for that we are going to define the function here, which is called grow tree. Okay, I can explain here. It's an easy part here, because we are calling the recursively here. Okay, so remember, we are at some point of a time we are at some node. So that node is denoted by the training data points, right, and corresponding label. So we are at some point of, at some point of time we are at some node, and that node is actually represented by some key. So root node is represented by key 0. So their child will be represented by 0 and 1. If, right child will be 1 and left child will be, sorry, right child will be 2 and the left side will be 1. So if we take one the childs of the node 1, then the childs will be 3 and 4, right? So it's just the twice of that node plus 1. So remember, if we are at the node 10, then its child will be 21 and 22, just twice of that key plus 1 and plus 2. So left node will be the twice of key plus 1, and the right child will be twice of key plus 2. Okay, so for any node will be denoted by some key, and starting from 0, root node will be denoted by the key 0. Okay, so now we are at some node, and so we have to find the entropy for that node. So we are taking the proportions of the examples in that node which belongs to class 1, right? So we are taking from that examples which belongs to class 1 and taking the proportion of the total. So this is the proportion of class 1 example in that node. We are finding the entropy of that node, and we will call it a pure node when will entropy goes to 0, and we are setting some threshold here. That's it. If the entropy is very less, or say very close to 0, you can set it entropy as 0.1, whatever you wish, where you want to stop splitting, right? So this is a threshold that we have defined to split to stop splitting. Okay, so once I found the entropy for that node, if it is less than this number, this threshold, then I will just store those node in our tree. So in that tree, I will be denoted by key. Key will be that node key, and that key will be the values, corresponding value will be, I will state that node whether it's a leaf node or the internal node. So if the entropy is less than this one, I will not split it further, and I will call it a leaf node. And if it is a leaf node, I will just tag it with the labels, and label which we got the majority one, right? And so those pure nodes, or the leaves nodes, will be denoted by their leaf and their label. And what will be the label? Label will be the majority. So if the in the training data set, if the class 1 examples, right? So in the, remember this one, if in the training data set, if the class 1 examples uh, have the higher proportion, I mean the have the proportion more than 0.5, it means the class 1 examples are more in that, in this particular node, and that means that the label will be 1 for that leaf, otherwise the label will be 0. Okay, so for that node, if the entropy is 0 less than 0.5, I will store that node as a leaf node, and its label, right? So for from key number, I can from that dictionary I can, if I get that key of that particular node, then I can tell whether that's a leaf node or not by just taking out that dictionary from that key, using that key. Okay, so this is when that one is a key, that node is a pure node. If it's not, entropy is not less than 0.5, what we will do, we will split it, right? Making use of that function that we have already defined. So I will call this function now for that particular node, right? So node is denoted by again the data set here. So for that particular node I will get the best feature, best value. And okay, so here I've returning ig best as well. So I will get the best feature, best value to split that node. Once I have those values for splitting that node, I will store those values for that particular node. Remember in the pure nodes or the leaves node, which is store the labels, because we only want the label for the leaves. But for the internal nodes, we have to split it. So that's why and we are storing those information for which feature and for which value we are splitting that node. So we are storing for that particular key node, we are storing its internal node. And another thing that we are storing is the best feature, best value uh, that we can use to split that node, right? Once we have those split point, now we have to split it and split that node, and we have to call those function again for that child nodes. Okay, so for that we need child nodes. So now here we will get the child node. So left x I'm calling at the data points in the left node and the corresponding label left y. And similarly in the right node will be the right x and the corresponding label will be right y. Okay, so in the left node I will taking only those indices where the training data set value for that feature is less than best this value, right? So all those all those examples for which the feature value is less than this value will go to the left node, and all those examples for which the feature value is greater than this value will go to the right examples, right? So that's how I'm collecting the examples in the left node and the right node. Once I have the left node, right node, I will again grow the tree from that point of, right? Now the key has remember this key was the key of that parent node, right? Now for the child node, left child node key will become twice of that key plus one, and for the right node the key will become twice of key plus two, right? And we will call this function again. It will iteratively will keep on calling till this will return the leaf node, right? So each and every node will keep on splitting till it becomes the pure nodes. And remember, we are calling it recursively, so it will keep on calling the function till it becomes the pure nodes when it stops splitting the nodes, right? So any doubt in this code? Okay, so not, if not, we can move to the next part. So it should not, it should be the easy part because we have already done in week 7 the same thing I've done here. Okay, so like grow the tree for x and y here. This starting from the root node. Going wrong here. Give me 1 minute. Something going wrong. Okay, so that was the problem here. We were giving a float value here, but it is taking only integer value. Remember here, uh, we have used so the split and for growing tree. Yeah, here this one. Here we will initially we were giving that float value. We can take some different number of parameters. So it is the number of feature that we are going to use here to split our data points. It's generally the root square root of the number of features. I'm just setting with the 5. It won't affect the answer much. So remember, this is how your tree is getting grown. Okay, and let me call this function for global tree, global functions. There would be any if there is any float value coming around this at this point, it's taking as a float value here that cannot be passed to this function, this choice function, right? np.random.choice function in the basic that we have defined here, maximum number. So that is why it is showing the error of the float value. We have set it to some fixed number, integer number. Now it's working correctly fine. So that is how you grow your tree, full tree, using the dictionary, where you store every information about every node in the node, right? Okay, so this is how once you have grown tree, you have to make predictions for every and each and every data points. So that is how we are defining function called predict, which takes the model, which is a tree. It takes the point x and the index at which it's currently present, the node at which it is currently present, right? And we will keep on traversing this point from the root node to the root node to the leaf nodes, and we'll check where it is going. Once it reaches to the leaf node, we'll make the predictions using taking out the key from that leaf node, right? Because remember, in the leaf node we are taking two things: one is the state, and another thing is the label. So from there we can take out the label. So we will calling the tree function for that particular node. So that node denotes at which node this x is. Once we have taken that key, we'll check whether it's a leaf node or the internal node. If it is a leaf node, then we'll just return that label for that, right? If it is not leaf node, we will split it according to the question. So we'll take the question will give you two values: one is the best feature, another is the best value at which according to which it is being split, right? So once I have those values, feature value, index, and the split point, I will just traverse it to the its child. So if this feature value is less than that value, then it will go to the left node. So left node is denoted by 2 times index plus 1. And if it is not, it goes to the right node, then the index will become 2 times index plus 2. And I will just call this function again. If it is a leaf node, it will return the value. If not, again we'll call this function and keep traversing this point from the root node to the right child nodes, okay, to the leaves. So for every point, I will start the indexing from 0, and will traverse it to the leaves nodes. Okay, is that clear? Okay, I think that should not be a problem. Once we have make a predictions, we have the grown tree, we have the predictions for a new point. Now what we have to do for the bag, different bag, we have to train those m different models. We have to collect those models, and then we have to aggregate the results for every data points, right? This is how we do keep growing the tree. Okay, so I don't know why this is not giving the right answer. I write the same code. We'll check whether this what's going wrong here. Some silly mistake I'm done in this code. So I'm just copying pasting the right code here to make sure that it doesn't go wrong. Give me 1 minute. So this function was not working correctly. Mm, correct it. Now I think it should work. Not now. Some mistake is going on because remember when I calling this function, is just giving me one node. It should give each and every node. Not sure where I'm going wrong. We'll check it and we'll let you know where I'm making the mistake. Should give each and every possible each and the state of each and every node, whether it's a leaf node or whether it's an internal node. But now it's giving me only the internal node position, right? Not sure why. Check that. So the code will work in the same fashion. Uh, so doing mistake in setting some parameters. Not sure what parameters. I mean the global parameters. Nice. Thank you, Suki. Now it's working fine. So you can see here for a particular, if I start with the zeroth node, I mean the root node, it will give me the position of every node, whether zeroth node is a leaf node or not. So zero is the internal node where it is split according to 20th feature and this value. Similarly, it will keep on traversing where some will become internal node and some will become leaf node. So what's happening in the prediction part? It is start from the leaf node. So if I make prediction for the first point, and it will start from the root node, right? The index will give the key for that particular node. It will start from the zero root node, and it will check whether zeroth node is a leaf node or not. It's internal node. So what we will do, we will split it according to this feature and this value. Once we'll check whether it is going into the left node and the right node. So we will take out this feature and this value from using these keys for that dictionary. Once if it is going into the left key, I will again call this function. If it is what this function will do now, it will check whether the left node is a leaf node or not. If not, then it will again traverse it to the next part. So it will keep on traversing till it reach to the leaf node. Once it reach to the leaf node, it will give you the label for that particular point. Okay, so that is how I'm making the prediction for a particular node, for particular data point, right? So any doubt in in this part prediction? If not, now we have to what we have to do. Next part is easy. Once we have grown the tree, we have to train those different trees over different training data set, and we have already created the function for creating the different data set that is called bag. So what bagging will do, it will take the entire data set and the number of bags we want, or say number of estimators we want. So we are setting the a global variable here, where we will store those m estimators or m decision trees, right? So I will start with the entire data set. I can start with the bag itself. So here I can also call bag here. Okay, so generally I will start with the training data set, and for for using this data set, I will grow my tree, and once I grow the tree, I will just append that tree into my list. Once I've grown this tree, I will again replace my training data set by some different training data set, which is I will call the function back. So it will create now new data set for me, new back for me, and again I will grow one tree and will append in this tree, right? So in such a way, I will create m different trees and will store in the list and will return these trees. So what this function is returning me is returning just m trees to me. If I call this back function over x and y, and I want six uh, uh, estimators, six decision tree, so this will give me a list of six models, six decision trees. Okay, now how to make the prediction in bagging or random forest? I will just take the majority. I will make for a particular data point. I just take the output for from all these m estimators and will check which is the major one. Let's say for a point out of 100 decision trees, 50 are 60 are making prediction one and 40 are making prediction zero. Then I just take the majority, right? So 60 are making prediction one. Then the prediction for that particular point will be one. I just take the majority, right? So for Dex here will be give me the list of will give me the list of models, a list of estimators, or say list of region trees, and that particular node for which I want to make the predictions. So for I will just store those predictions here. I'm initially calling the prediction as zeros, and how many predictions it will store, how the number of estimators we have, right? So and now I will check for every estimator. I will just make the predictions using that function predict. It will take that estimator and the point and will start from the zeroth root node, right? And I will store the prediction in that ith position for this list, this array, and we'll check the majority one. So I will check where the sum of the count where it will give me the count of number where the predictions was one, right? And if it is greater than the half of the estimators, right? If out of the if for example, if there are 100 bags, if the out of 100 bags more than 50 has given predictions one, then the major prediction will be one. So the final prediction using the random forest will be one, otherwise the prediction will be zero, right? So this is how I make the prediction using those m different estimators. Okay, so this is for one example. Let's call for the very first example, it will be zero, and for the 20th example, it will be one. So if you check the actual here, so initially some values are of belongs to class zeros and then class one. So if you can also find the accuracy as well for every. So you have to make predictions for each and every data point here, then you have to store them those values, and you have to check whether they are actually correctly classified or not. From checking that, you can easily make the easily can find out the accuracy for the training data set using those m estimators. So remember, in this particular data set I just trained six models, right? And over six models, I have found the output, and only those six models are giving me very good output. You can verify it as well with just finding the accuracy, because it's a very toy data set. For this data set, even very less estimators will work for you. Even a decision tree will work for you. Will work very well for this particular data set. But when the data set becomes very I mean, it's not very toy data set, then in that case you may have to train more number of estimators, right? So any doubt till in bagging in random forest? The only tricky part here was to grow a decision tree. Once you have grown the decision tree, you just have to grow those trees over different training example. That's it. You are done. So only code was here was to grow the tree, and you have already seen this how to grow a tree in week 7 as well. And now I have already repeated that. So if you have any doubts in this, you can ask. Otherwise, we can move to the ADA boost problems. Okay, so let's move to the ADA boost. So what happens in ADA boost? In bagging, we train M estimators, but those estimators don't interfere in training part, right? We can train each estimator independent to each other, so we can train them parallelly, right? But in the boosting, what we do, we start with a weak learner. And what is a weak learner? Weak learner is one which tends to underfit, or say weak learner are one whose performance is just better than the random guess or so random estimator. So we start with a weak learner. We make predictions of the training data set and check how it performs on the training data set. Based on the performance, the error it makes, we create a new data set, and we again start training a new weak learner over that training data set. So only difference here is that we iteratively train our models, and the models which are used here are the weak learners, the ones which have the high bias or call which tend to underfit. Okay, so generally the decision stumps are used in the boosting, and or say decision systems are used in AdaBoost, and different algorithms are there which make use of different estimators, but generally decision systems are used in the AdaBoost algorithm. Okay, so we start with a weak learner, then we check the performance over the training data set, then we create the data, we create the another training data set, and to create the training data set, we increase the weightage to the incorrectly classified point and decrease the weight for the correctly classified point, and those weights we use as a probability to come into the next bag, right? So remember, in the very first bag we just take every examples to be equally probable to come into a bag, right? While to create the next data set, we increase that probability to come into a bag for the incorrect, we increase the probability for the incorrectly classified point, and for the correctly classified point we decrease that probability. Okay, so only difference here from the bagging is that we have to, the bag that we create should have different probability distributions to be in the bag, right? So for the only thing that will change here is that the bag, right? So here I'm taking the same data set. Okay, so I'm taking that same data set, but the labels I've changed to the -1 and 1. Initially it was 0 and 1, so it won't affect much. And the entropy, the same thing for the measure. Okay, so so let's go. Let me first define the bag. Okay, so bag here, what we there we have done, we have taken the probability distribution to be the uniform distributions. Every examples were equally probable to come into a bag, but here the distributions will change every time. We will have different distributions. So that distribution we have to give here. So these are the weights or called probability distribution. So every data point have different chances to appear in a bag, right? Depending upon how much error it may, how much whether it is correctly classified or not by the previous estimator. So according to that, that weightage may increase, may decrease, right? Okay, so this is how you create your bag in the AdaBoost. The same code, but just the probability distribution has changed to some weightage, right? And make you have to make sure that these weights actually should sum up to one. Okay, so that we will take care of. Now we have to grow a decision system. So decision system is nothing but the node with one split only. So it's just we have to take a node, we have to split into the best part. So that we have already seen the best feature and best value we have to take out. So all these things we have already done in the previous part. The only difference is here, because we are splitting only once, so we are taking out the labels from the left node and right node. So once we have the best feature value, best value to split, I will just take the example in the left node and the right node, right? So this will give me the left the examples in the left node, and this will give me the examples in the right node, and I will make the prediction in the left node. So majority I will count. So if the count the measure example belongs to class 1, then I will just make the label as 1, otherwise label as -1, right? Similarly for the right node, if the example belonging to class 1 are of majority in the right node, then I will label for the right child will be 1, otherwise it will be -1. So what I've done is I just split the node according to the best information gain, and just divided the data set into left node and right node, and just take the labels out of it. Okay, so now my decision stamp is actually giving me the labels for the the best feature, best value, and two more things I've added: the label for the left node, the prediction for the left node, and the prediction for the right node. These two things added extra here. The same code I've written that we have written for the best split, right? Now I need not to grow the full tree because we always use the decision stem in the ADA boost. Now I have a model, and so how to, so this will be my decision stem now. Okay. So how to make the predictions? In this case, I just traverse it to the two parts, whether it belongs, that point belongs to left node or right node, and I will take the label from it. So first, this is our model. From model, I will take all those values, features, best value, left label and the right label from that model. And for every x in that, now x is now not a just single data point; it's a matrix of the data point. So I will take every data point. I will check whether this correspond this feature and this value are less than or greater than. If it's greater than this, it will go. The prediction will be the right predictions, right? Because it is going to the right label. And if the feature the x value is less than this value, it means that it is going to the left node, and the predictions for that will become the right label, left label. Okay, so I'm just checking whether that point is going to the left node or right node. According to that, I'm giving the prediction for that point, and just I'm returning prediction for each and every data points here. Okay, so that is how I'm making predictions for our data set X. Okay, so I have a model. Now I have the predictions to make using that model. Once I have done this, and back I have already defined. So now this weight I am to come up with how to increase the weight for the incorrectly classified point and how to decrease the point for the correctly classified points, right? So for that I have to update weights, right? So how to increase the weights? We calculate the alpha values, right? So alpha will be what? It will be 1 by 2 log 1 minus error upon error. So error, how much error it makes on the training data set, right? So I will find the error. So it will be the prediction for that data set using that stump, and this is your actual level. So I will check whether I will check the proportion of the points which are incorrectly classified. So this will be my error. So this will give me the count where they have incorrectly classified. So proportion I will take, this will give me the error for that particular data set. Once I have taken error, the alpha value will be 1 by 2 log 1 minus error upon error, right? So this is my alpha. And for update weight, what I will do, so let's call W with the initial weights or the weights of the previous estimator. For the next update, what I will do, I will just increase the weight by e raised to power alpha for correctly classified point, or for incorrectly I will increase the weight by e raised to power alpha, and for incorrectly classified point I will just decrease the weight by e raised to power minus alpha. So alpha, I've just taken the same code here, whatever I've written here. The same I've written for finding alpha. You can make use of the function definition inside this function as well. And I just increase the weight with e raised to power minus alpha and alpha. So this is expression makes sure that it's alpha when it's correctly classified, and e raised to power minus alpha when it's correctly classified, right? And to make sure that the sum becomes 1, I just divide the weight with the sum over all those weights, right? So it makes sure that the weight sum over all the weights becomes 1 to make it valid probability distributions. That's how I update the weights for each and every data points for the next batch. Next is the similarly iteratively I will train all those models. So here HI will store all those M models. Alpha I am storing just because in the making prediction, remember we take the weighted average, not just average. So I will just store those alpha values as well, right? So this alpha is called the performance of those models. So I will start with the initial weight with the uniform weights, right? Each and every data point will be given uniform weightage to appear in a bag, right? So this is my initial weights, and this is my initial training data set to train my very first model. So I will train my very first model. I will make predictions over the training data set. Remember, for uh, training the decision system, I'm making use of x train and by train. This is just the very first bag. but I'm making prediction over the entire training data set, the one which I will started with, right? And I will increase the I will compute alpha, and will just store those values into alpha I, alpha I dot append alpha I will append here, and that model I will train, whatever the model I've trained, I will store into hi I will store. Okay, so here in hi I am storing the predictions for the training data set. Okay, so hi I am storing the predictions, and alpha I am storing into alpha I. Okay, once I've calculated that alpha I and by prediction for a first model, I will go for the second model. For going to the second model, I will just update the weights for the every data points, the training data points, right? And I will now use, I will create now next bag. For next bag, I will use this updated weight, right? In the definition of bag, we have defined this initial weight, right? So I will use now this weights or this probability distribution. Okay, and what it will return, it will return me the predictions for every data points for every model, ith model, and the array of the those alpha values. So it will give me how many okay, so I have here trained 20 models here. So it will give me the 20 predictions for each and every data points, and 20 alpha is for 20 models. And how to make the prediction? The prediction is just the weighted average. So alpha is my so for every any data point here x and y, I will take the predictions from that model, random forest model, and every m models, and alpha will be my that alpha value. So I will just take the weighted sum here, and will uh, I will just return those. So this weighted sum will give me values 0 or 1. Right? Remember. So 0 means just replace it with minus 1, and 1 to 1. So I'm just taking 2 times of x minus 1. So it makes sure that if it is 0, then it goes to minus 1. And if it is 1, it goes to 1 again. Right? So this is how I'm making the prediction. So if you do over the training data set, whatever the data set we have defined, you can see that accuracy is coming out to be very, very low. It comes out to be zero point 0.0. It's very low. Even if you keep on increasing a number of estimators, may decrease to 0. So AdaBoost was not a problem. Once you have done bagging, you have AdaBoost is just you have to take for creating bags. You have to create different. You have to make sure that the every data point now have different weights associated with that. It's not just uniform weight, and all those things goes in the similar manner. Just training models in iterative fashion. So if you have any doubts in this algorithm, AdaBoost, you can ask. Otherwise, not, then we can close the session. No, it's the time of ensign. Yeah, you will be preparing for that, and after that, after the ensign, we will be having a workshop where we will discuss some of the machine learning techniques in details. If you are not following up on that assignments, you can do it after the ensign exam.
Hello.